Assalamu alaikum. Laplace transform has some specific properties, and in this video we will discuss about two properties of Laplace transform. One is linear property and another is scaling property. So at first let's see the linear property of Laplace transform. Now let's understand this property with specific example. Suppose s of t is a function which is the combination of these three functions, which is also the functions of variable t, means this is a function where these three functions are combined. Means if we break these functions, we will get these three functions which added with the sum. So as these three are also functions of t, so if we do the Laplace transform of this main function, then the Laplace transform of this s of t will be Laplace transform of these functions, and if we break down this Laplace transform with each functions, then we will get Laplace transform of these our first t functions, Laplace transform of our second function, and Laplace transform of our third function. And c1, c2, c3 are arbitrary constant here, they will remain same, c1, c2 and c3. We know that arbitrary constant will not change. So it is very easy. We already have how to convert a function into Laplace transform. We will just add the Laplace transform for every function separately. Now let's see an example. Here in the example there is a question where we have to find the Laplace transform of this s of t function. But this s of t equals to 2t square plus t, means it is a function of t and it is another function of t. Suppose this is our a of t, means a function of t, and another function will be b of t. Here arbitrary constant 2 or here arbitrary constant 1. So let's do the math. If we here want to find out the Laplace transform of this s of t, according to this linear property, we will Laplace transform separately for these both functions. So here arbitrary constant will not change, this will remain same as in the questions, and then the main function is t square. So we'll do the Laplace transform of this t square, Laplace transform of t square, and our second function is t. So then we'll took another Laplace transform of these t functions. Now we will do the Laplace transform of this and this separately, and then add these two result. If you see the playlist of Laplace transform, in the second video I already have discussed about this functions Laplace transform. If our functions is t, then the result after doing the Laplace transform will be 1 divided by s square, and the result of t squares functions, the result will be 2 divided by s cube. This can also be solved using this equation formula. With the help of this, I will put the value of the Laplace transform of these two functions directly, but you have to do separately Laplace transform this from here, as I already have done this, so I will not write again the same thing, so I will just put it here. So our arbitrary constant will remain same, and the Laplace transform of t square will be 2 divided by s cube, which we can see from the previous video, plus Laplace transform is 1 divided by s square, and if we multiply this, we will get s divided by s cube plus 1 divided by s square. This is our required the answer of our Laplace transform. After we do the Laplace transform of this function, we will get the answer of this. Means it's just similar with the basic Laplace transform. We will just break the Laplace transform for each and every functions. Now our another property of Laplace transform is scaling property. It's also an easy property of Laplace transform. Suppose f of t is a functions which is a functions of t, and if after doing the Laplace transform of this function, suppose we will get the answer as a function of s. As you can see, after doing the Laplace transform of t square, we get 2 divided by s cube, and look at this, it is a function of s, and if we do the Laplace transform of t, we will get 1 divided by s square, means it's also a it's also a function of s. So after doing any Laplace transform of any functions, then we will get the result in the functions of s. So universally we write here that if f of t is any functions, and if we do the Laplace transform of this function, then we'll get the result which is a function of s. So we can find this from the basic formula of Laplace transform, or using this direct formula you can also write here. Now let's see what this scaling property says. This scaling property says that we already know this from the basic formula of Laplace transform, and if there is a function which is similar to this but there is an extra constant which is multiplied with the variable t. If our function is like this, a can be any constant, any arbitrary constant, and if our given function look like this, we will find the result from using this. But here is a small difference, is we will divide the result with this constant, and in the functions there will be also, the whole functions will be also divided by this arbitrary constant. Let's see an example to understand it more clearly. One example is, suppose we know that, suppose f of t is a function of e to the power t, means it is a function of exponential functions, and we know the Laplace transform of this e to the power t equals to 1 divided by s minus 1, where s is greater than 1, because if s is less than 1 then it will be infinity. So after we do the Laplace transform of t, we got this. And suppose our another function is f of 2t equals to e to the power minus 2t. So then our required given functions will be e to the power minus 2t. Look at this. Here we have e to the power t functions, and here we have e to the power minus 2t functions. Here the difference between these two functions is only this minus 2. Means we multiplied these functions with minus 2. Means our arbitrary constant is this minus 2. So according to this scaling property, our Laplace transform of these functions, using this result, we can write similarly like 1 divided by constant. 1 divided by, here our constant is minus 2. So 1 divided by minus 2 into f of function of s by a. Here this is the fs functions. So now here we'll put the s divided by constant where the s remains. So our final result will be 1 divided by minus 2, and here we will write 1 divided by s divided by minus 2 minus 1, means where our s stays there I will write the s divided by constant. This is our scaling property. So if we further calculate, we will get 1 divided by minus 2 into minus 2 divided by s plus 2. Here we have done this calculation. So this minus 2 will be cancelled out, and our final result will be 1 divided by s plus 2. Now let's see, is this scaling, using this scaling property, the result we got 1 divided by s plus 2. Is it correct? Now we'll do the Laplace transform of these functions manually. According to our formula, we'll write integration of 0 to infinity, then these functions, means f of t functions, e to the power minus 2t, and in formula we have e to the power minus st into dt. Why it always f of s functions? Because in the formula we have a function of s. So yeah, now if we integrate, now we will do the process of integration. Integration 0 to infinity will simplify this because both are exponential function, so we can sum the power of this because they are same base. So if we add this, so minus 2t minus st into dt. Then if we further simplify this, it will be 0 to infinity e to the power, if we took the common minus t, there will be remain 2 plus s into dt. So now we will integrate these functions. So if we integrate this, we will get e to the power minus t2 plus s divided by minus 2 plus s, and here our limit is 0 to infinity. Now we will put the limit, and we remove this from the limit for making our calculation more easy. So write e to the power minus t 2 plus s 0 to infinity. Now we will put the limit in our functions. So at first we will put this higher limiting value. So if we put the higher limiting value, we will get e to the power minus infinity, because instead of this t we will put this infinity. So minus infinity into 2 plus s, and if we multiply anything with the infinity, the result will be also infinity. So we got e to the power minus infinity minus e to the power 0 into, we will put the 0 instead of this t. So our whole result will be 0. And e to the power minus infinity equals to 1 divided by e to the power infinity, and 1 divided by something infinity equals to 0. So our ultimate result will be minus 2 plus s into 0 minus e to the power 0 means 1. So if we remove the first bracket, we will get 1 divided by 2 plus s. Look at this. From the using this scaling property, we also get 1 divided by s plus 2. And if we do the manually Laplace transform, we also get the same value. So our scaling property is proved, and using this scaling property, we can easily do any function's result using the Laplace transform. I hope you understand these two property of Laplace transform. Let's see another example of this scaling property. From our third video, we have already proved that the Laplace answer of Laplace transform equals to s divided by s square plus 1. Now suppose we have to find out the Laplace transform of function cos bt. Means here is the difference of these two functions is only this arbitrary constant b. So according to this scaling property, we will write the answer. So at first we will write 1 divided by constant, means 1 divided by b, into where s stays, we will write s divided by constant. So at the upper we will write s divided by b, and here s divided by b and whole square, because we just write s divided by b instead of this s, and the square will remain same, plus 1. And now if we simplify this, we will get 1 divided by b, s divided by b, or s square by b square plus 1. b to s divided by b divided by s square plus b square divided by b square. So further if we calculate, we will get s divided by b into b square divided by s square plus b square. So this b and b square will be cancelled out, and our final result will be s square, sorry, here remains just s divided by s square plus b square. This b and b square will be cancelled out. Our result will be s square plus b square. This is how we can use our scaling property. I hope you understand.